Hello again. We are continuing our discussion of section 2.8. We just finished up our initial discussion of linearizations, although they are going to come up again in this worksheet. But now we're going to change gears a little bit and talk about what are called differentials. Now, the idea behind linear approximations are sometimes formulated in terms of the differentials, which we write as dx and dy. So to understand what dx and dy are, let's consider the points in the figure on the right. So we have the point P, which is this point here. That is the point x, f of x. We also have the point Q, which is here. And this is associated with a slight change in x plus f of x. So that's going to be the point x plus, delta x. I said that wrong a moment ago. And the y value then is going to be x plus delta x substituted into f. So Q is x plus delta x, f of x plus delta x. Now we wish to use the linearization, which is that blue curve, of f at the point P. So it's generated here at the point P to approximate f of x at the point Q. So notice that if we were to substitute this x plus delta x value into our linearization, we would actually get to the point R, not Q. So essentially what we're doing here is we are saying that the point R is approximately equal to the point Q. R is the point that we get from our linearization, Q is the point that's on our function. Now, in the figure, this might look like a pretty good distance between, but we also may have just zoomed in a lot on the figure in order to get that large distance. Now, the exact change in y, if you move from the point x to x plus delta x, then the exact change in y is going to be the exact difference between the function values, f of x plus delta x minus f of x. However, the change in our approximation is going to be the distance, or I guess the vertical distance, between the points R, which is our approximation, and the point S. Now, if we draw that triangle down here, we have the point S, we have the point P, and we have the point R. We are wanting to know what the rise of this triangle is. The horizontal distance, or our run, is delta x, and we also know that our slope is f prime of x. Because we're talking about the tangent line approximation, the slope is f prime of x. So we can find the change in y by multiplying the slope by the change in x. So this means that our vertical distance between r and s is going to be delta x times f prime of x. So we are going to define the differentials dx and dy. Let's see. This is a definition as the change in x and the change in y for our approximations. So dx, the change in x, well, that's really the same both times, whether it's for the change in the function value or the change in our approximation. So that's going to be delta x. And the change in the approximation vertically, as we already saw here, is delta x times f prime of x. So delta y then represents delta y. This is the exact change in y. This represents the amount that the curve y equals f of x changes when x changes by a small amount, delta x. Whereas dy, this is our differential, represents the amount that the tangent line, or the linearization, changes when x changes by the same amount. Now, as long as f of x is close to the linearization value, then the exact change in y should be close to the change in should be close to the differential dx. And so just as we used the linearization to approximate function values, we can use the differentials to approximate the change in the function values. And that is all we will have in this